esters, which is the main component of biodiesel, from soya acid oil, which is a byproduct of vegetable fining, by sulphuric acid, catalyzed esterification using ethanol. And my contribution to that academic fraternity was the use of robust design methodology, which is method developed by Genich Taguchi, referred to as the Taguchi DOE design of experiment. And I was also investigating the use of ethanol as my standby alcohol. My analyzing principles, scientific principles, were basically esterification and transesterification, which both involve the reaction of a carboxylic acid. Actually, esterification is the reaction of a carboxylic acid with an alcohol in the presence of an acid and a mineral acid to form an ester medium, which is the RCO4R. And then transesterification is a similar reaction, but it is just the reversal. It is just the removal of an alkyl component, in this case R2, and replacing it with another smaller alkyl component, be it ethanol or methyl alkyl component. So my specific objectives is, according to the project today, to obtain and prepare a sample of soya acid oil for acid catalyzed esterification, and then to investigate the effects of those 5 parameters, those being temperature, agitation for each, reaction time, fatty acid to catalyst floating ratio, and ethanol to fatty acid ratio, and then to obtain conversion as a measure of the objective function, and then to quantify the use from the design experiments. So the drive for this particular investigation primarily lies in the production of soya acid oil. It is, you cannot avoid producing soya acid oil because it comes as a byproduct of vegetable fining. So when we are producing oil from soya beans or from cotton beans, from cotton seeds, actually, you actually come up with a product called soft stock. Soft stock has to be acidulated because you cannot dispose it as it is into the environment because it contains a high number of fats actually. So it goes through a process called acidulation, and that acidulation costs roughly about $1,200 per ton. And it cannot be directly translated to any value product. You ask for you. Currently, only the industry is hosts about 700 tons of this byproduct, which they have not yet found a working solution for. So, besides that production of soya acid oil, the other reason that the other drive actually was because it contains fatty acids. It can be actually converted into biodiesel, which contains fatty acid ethyl esters. It can be converted into esters by reaction of that fatty acid component with your alcohol, and that has got significant, or that can actually come up with significant returns for the parent companies, whereby you've got petrol diesel costing an average of $1.37 per liter, with associated benefits of sustainable development as well. So, like I said, my design of experiment was based on the Taguchi design of experiment. The benefits are accruing being robust design and the experiments. And then I used the L16 4 to the 5 orthogonal array, whereby I got 5 factors and 4 levels. And then I was running them in duplicate because my main factors were temperature and humidity. And that right there is the table that I was using for each and every, that defines the factor in each associated level, whereby temperature was ranging from 50 to 80, and actually speed from 900 to 1,500, as can be seen on that particular table there. The methodology that I employed was to investigate, or my objective function actually was to investigate the percentage conversion of the free fatty acid component of the acid oil, and I was using acid value as my measure of the free fatty acid component present. That is the method that I was using, and that is the equation that is used, developed by the American Oil Chemical Society. And the scientific principle behind the AOCS method is just simply to obtain the value or the amount of sugar hydroxide that is used to neutralize the free fatty acid component present. And then I borrowed the method of G. Cholakov and Esterification of 2018 for my methodology, which included a flux condenser where I was adding my reactants defined by the table that I showed you into the three-neck round bottle flask, and then allowing it to react for the specific time, ranging in between 1 and 4. Again, according to that particular table that I showed you, I had a shell panel which I was using to make up my ethanol. As soon as I realized that my temperature was going beyond the temperature that I needed, it would mean that my ethanol was running up, so I would heat up extra ethanol. My ethanol was 99.5%, and then my sulfuric acid was 98% sulfuric acid. The reflux condenser was simply to reflux, as we can all see, as we all know. And then statistical analysis for the Taguchi method. I just needed those two particular values, which were my mean conversion. Since I was doing two experiments, I needed a mean value for my conversion. And then since I was looking for a larger conversion, I also required, or I actually chose the larger temperature performance criterion as well, as defined by Genich Taguchi for the calculation of the signal to noise ratio. I also went on to do an ANOVA analysis of variance to obtain the differences between the means in between my samples. And then that p-value here was just used to show if my variation was significant or not. So it would, that's basic statistics. Having done that, I calculated my average moisture content and then obtained 2.845% as my moisture content, and then my average initial acid number was 193.29 milligrams of chloride hydroxide. This is the results table for all the experimental runs that I went through. So I only included quite bad, they being my average mean for the two runs that I was doing. And then my results now for table 2, which shows the order of influence of my factors on conversion. So the statistical analysis that I went through allows us to actually see which factors affect your conversion more than the others. And in this particular instance, they were in that order: temperature, time, agitation, speed, catalyst load, and the alcohol to acid ratio. Now, in discussion, I would want to point out that they were actually in agreement with what is to be expected from theory. Temperature is a strong correlation with your kinetics constant, and it also reduces the phase separation between your aqueous mineral acid and your fatty acid component, which is your other reactant. And then your time of reaction, obviously, if your time of reaction is increasing, it definitely means that there is a greater propensity, a greater probability actually for successful collisions. Agitation speed was actually a trade-off between vortexing, which is a result of too much agitation, which therefore reduces the amount of turbulent motion required for successful collisions, and insignificant or insufficient agitation, which actually defeats the entire purpose of reducing phase separation. The catalyst that I chose, being an acid catalysis reaction, it is actually 1,000 times lower than base catalysis, is presented by Edgar Lutero of 2005. So it compared actually with my studies here, which showed that it was number 4 on the rank of influence. And then the alcohol acid ratio as well was determined by the molar reaction ratio. And then this table here, the main effects plot, just goes on to show you the outcome condition that would be required for me to obtain maximum conversion. So they are stated over there. Temperature is 80 degrees, agitation speed is 900 joules per minute, and then you've got 9 to 1 alcohol acid ratio, and then 0.7% catalyst load, and your reaction time of 4 hours was obtained. And then this is another table which just goes on to show you that at the 95% confidence level, all means will vary significantly. Is defined by the p-value over there, which all values are greater than 0.05, which is since I tested at the 95% confidence level. So it shows that all your values are greater than the means actually vary significantly. So using the optimal conditions that I realized that you can actually get a maximum conversion of 89.4% from the Taguchi method. So this here is the summary of what I went through and everything that I have explained. I might just need to point out the recommendations that I brought here. For this particular study, that we need to develop a flow sheet and then to do a detailed economic feasibility analysis. And then you can also go through methyl sulfonate synthesis using the acid oil, the acid component of the free fatty acid as well. But in this case, you'll be using methanol instead of ethanol. And then you also need to investigate the effect of water, since this is an esterification reaction. As we know that esterification is an equilibrium reaction. So the formation of water or the addition of water would actually reduce the amount of, or the conversion, the maximum conversion that you attain. And that concludes my presentation, why attracting persons on the floor.